Hey guys, welcome to AI Tech Talks with Carl. Today we're going to install and use the C API for the XGBoost model. Since the XGBoost package in Python uses the C API to actually train and make predictions, using the source functions in the C API is actually quite a bit faster than Python. Now, the documentation doesn't give a great tutorial on how to use it, so I'm going to go through exactly how to install and use the package and train a model on a simple data set. So let's go ahead and get started. The first thing that we need to do is get to a Linux machine, since building the object files and libraries for XGBoost is meant to be done in Linux. For this, I'm going to use Windows Subsystem for Linux, or WSL, which is really nice for getting a Linux environment on a Windows machine. I'll put a link in the description below to be able to download that and use it for a Linux terminal, but essentially all you need to do is type WSL install in the PowerShell of your Windows machine. Next, we can go to the documentation for XGBoost by DMLC and find the section on XGBoost tutorials, and specifically the C API tutorial. One requirement of XGBoost is installing a software build system called cmake, which allows us to run and build our program by using a cmake list.txt file to perform computations. So this is essentially a tool to write large make files that run G++ compiler commands, which create object files and a shared library.so file. So let's do that by running the sudo apt install cmake command, which uses the advanced package tool in Ubuntu to install cmake. Now, another requirement in the tutorial is going to be to use conda and create a virtual environment to install the include files and shared object library in that environment. So this isn't actually required, and I don't find it useful to download Anaconda and learn all the commands to make a virtual environment. So we're going to skip this step, and I recommend that you do the same. Now let's download the GitHub repository by using the git clone -- recursive command in the home folder of the Linux shell. After downloading it, we see that we have a folder named XGBoost in the home directory, and from the instructions that we can cd into that directory. The cmake program uses a build folder to save all the necessary information for compiling and installing, so we have to make a build directory in the XGBoost folder. We do that by saying mkdir build, which makes a directory called build. We can see this folder by using the linux ls command to list all current directories. Since cmake requires that we have to be in the build folder to run the program without specifying a build directory, let's cd into the build directory. Now the instructions in the tutorial say to activate the conda environment in the next step. We're going to skip this step as stated before and instead just not use a virtual environment. So the next step that we need to do is actually run the cmake program to generate a make file by calling cmake and giving the directory where the cmake list.txt file is located. So since that file is located one directory up, the tutorial says to use ... and provide it with a cmake install prefix to the current conda environment. Again, we are just not going to use conda and thus not even provide a cmake option with -d. This will just install the necessary header files and shared library in the default location for Unix. So if we go to the cmake install prefix documentation, we can see that the variable will be prepended onto all install directories. So that's why they use the $conda prefix variable for the prefix. When nothing is provided with the -d option, then the variable will default to user local on Unix, which is where all the other standard C libraries are kept. Let's go ahead and run the cmake command without any install prefix, and this will generate a make file in the current build directory. All the build and make files can be seen with the ls command to confirm it works. Then, since we are installing files into the root location on Linux, we have to use a sudo command on make install, and it should compile and install the files to the user local directory. Now that we've installed the necessary components to use the XGBoost shared object library, we need to actually write a C program to use the C API. Since the tutorial uses cmake to build the executable, we are just going to follow that because everything is already done for us. We start by making a cmake list.txt file in our project directory. So first, let's make a project folder called CAPI demo to put all of our files in. Then we can use a cmake list.txt file in that folder to write our cmake program. For this, we can basically use the code that they gave us, but I'll explain a little bit about it first. We name the project with the project command, and this will be the same name as the executable that we are building. Let's just name the executable demo. We don't need any versioning stuff in our project, so we can delete that, but we will leave the language bindings of C and C++ in the command. Then cmake will find the package with the configuration files that the XGBoost authors wrote to be able to locate the correct folders. We will then add the executable, which creates a binary file called demo from the .c file that we wrote, and finally link the correct libraries to the target executable that we are generating. I'm just going to call the .c source file as demo.c to make it easy. Before we go any further, we have to make the demo.c source file to use the C API. I recommend that you go over the tutorial because it briefly explains how to use the functions and data structures in the API. However, I will go over this demo.c file that I made to be able to train a simple model for classification. The source file that I made, located in the C API demo directory, starts off by including all the necessary C header files. We include the standard library and the C API header with XGBoost /CAPI.h. Then I copied the safe XGBoost macro from the tutorial to wrap the function calls in a macro that will print any errors that occur. Next, we can define a main function and declare two dmatrix handle variables called train and test to be able to put our data into a dmatrix. Then we can call the XGDmatrix create from URI function to populate the dmatrix with the contents of a file containing our training set. The tutorial says to use the XGDmatrix create from file function, but as in the documentation, this function is deprecated, so we can use the XGDmatrix create from URI function to get the training and test data. But what is the rest of this in the arguments to the function? First of all, the function accepts a config parameter as a pointer to a const char. This string must be the JSON encoded parameters for dmatrix construction. JSON notation uses double quotes to encapsulate parameters in curly braces. So we have to escape these double quotes with / double quote and define the URI parameter and a silent parameter. We set the silent parameter to 1 and the URI parameter to the path for our dataset. I'm using the dataset that the authors provided under the demo/data folder of XGBoost. My file is located in one directory up from where the executable will run, so I put .. in front of the file name. If I open that file and take a look, we see that it is in a different format called libsvm format, which is good for having sparse data. I put a link in the description below, but essentially each row is a training example with the first column as the target label of that example. Then to the right is every pair of feature index and value separated by a colon. This is very efficient for sparse data, which is XGBoost's whole thing because you don't actually have to load the zeros into memory. Going back to the demo.c file, we can put that file as the URI parameter with $format equal libsvm after to specify the libsvm format. Then we just set the silent parameter as 1 to not print any messages, and we pass in the address of the train dmatrix to the second argument of the function. We do the same thing for the test dataset named agaricus.txt.text to load the test dataset into a dmatrix. We can then create a booster object passing in an array containing the train and test dmatrices and the address of the declared booster object. I set the number of iterations equal to 100, and an array of the two strings train and test. The for loop runs over the number of iterations and calls XGBooster update one iter, passing in the booster object, iteration number, and the train dmatrix. This will update the booster object by one iteration by making predictions, getting the gradients for those predictions, and doing a boosting step. The last thing to do in the for loop is call the XGBooster eval1iter function, passing in the booster object, iteration number, the dmatrices to evaluate, the names of the datasets, the size, and the address of the char pointer to save the string evaluation result. Finally, we return 0 at the end of main. Now that we have our cmake lists.txt and .c source file, we can make a build directory in our project to let cmake do its thing and generate an executable for us. For cmake to work without specifying where the build directory is, we actually have to be in that directory, so first cd into it with the cd build command. We skip the conda activate step and invoke cmake by just using cmake ... which will search for the configuration files in common directories. It will find it in the user lib directory that we installed all of our files in. So essentially, we are following the tutorial because in the tutorial, cmake will search the same directories, but just within a virtual environment prefix from conda. We are providing it with no directories, so it will go straight to those directories without the conda prefix. Finally, we call the make command to build our executable, and this will generate the demo executable in the build folder. Let's check to see if it worked with ls, and we see the demo file with no extensions in this folder. If we run this file in Linux with // it is extremely fast while training and evaluating with a test set. Look how fast the training was. We can see that the log loss was printed for both the training and test sets, with the loss decreasing over the 100 iterations ran. So that's it for this tech talk, guys. If you liked the video, please support the channel by subscribing and sharing with your friends.